What is the surface area of a sphere of radius r divided by its volume? Is it 1 over 3r, 4 over 3r, 3 over r, or 4 over r? So the sphere has radius r, and we want to know what's its surface area divided by its volume. Okay. And how'd this one go? Everyone got this one right too. Very good. Nice. How'd you get that?
The surface area of a sphere is 4 pi r squared, and the surface area of the volume of the sphere is 4/3 pi r cubed. So the pi's and the 4's cancel, and you're left with an r on the bottom, and you're dividing by 1/3, so 3 on the top.
There you go. Very good. Nice explanation. The set pictured is named after which of the following mathematicians? Is it A, René Descartes, B, Pierre Fatou, C, Edward Lorenz, or D, Benoit Mathematician? We'll see what the answer is. I think everyone knew it, right? Very good. We'll let you know where we got that graphic, and then we have a little bit of an explanation about that set as well. Hold.
Hi, I'm Kathryn Lindsey. I'm a researcher in mathematics at the University of Chicago. My research is in the field of dynamical systems. The Mandelbrot set is a central object in my research.
To define the Mandelbrot set, we start with the notion of an orbit. The orbit of a point P under a function f is the infinite sequence obtained by starting with P and repeatedly applying the function f. Thus the sequence is P, f of P, f of f of P, f of f of f of P, and so on. For example, if f is the function defined by f of x equals x squared, the orbit of the point 2 is the sequence 2, 4, 16, 256, and so on. The Mandelbrot set is defined in terms of a particular family of maps. For each number c, we define a map or function, f sub c, defined by f sub c of x is x squared plus c. Thus, for example, if we wish to compute the orbit of 0 under f sub c, it is the sequence 0, then f sub c of 0, which is c, and then f sub c of c, which is c squared plus c, and so on. A complex number, say z, is something of the form a plus bi, where a and b are real numbers, and I is the square root of -1. We say that the real part of z is a, and the imaginary part of z is b. We can represent a complex number as a point in the plane whose coordinates are real part of z, comma, imaginary part of z. Now remember that family of functions, f sub c? The Mandelbrot set is the set of all complex numbers c such that the orbit of 0 under f sub c is bounded, or in other words, does not go to infinity. For example, if we consider the function f1, that's the map x goes to x squared plus 1, the orbit of 0 is not bounded, it goes to infinity. Thus 1 is not in the Mandelbrot set. In contrast, the orbit of 0 under the map f sub I, that is x goes to x squared plus I, is bounded. So I is in the Mandelbrot set. Here are some pictures of the Mandelbrot set. This is the whole Mandelbrot set. Then we zoom in and we look at certain regions of the Mandelbrot set in more detail. Here you can clearly see the fractal feature of the Mandelbrot set. It contains smaller copies of itself, each of which in turn contains smaller copies of itself. The complicated shape of the Mandelbrot set is both mathematically meaningful and visually.
While mathematicians such as Pierre Fatou and Gaston Julia conducted research in complex dynamics as far back as the early 1900s, it wasn't until the development of computer technology in the past few decades that mathematicians could really see the images associated with complex dynamics. The first image of the Mandelbrot set was created by Benoit Mandelbrot in 1979. Mathematicians Adrien Louady and John Hubbard established many of the fundamental properties of the set, and they named it in honor of Mandelbrot. The Mandelbrot set is the focus of a great deal of ongoing mathematical research, and there's still many unanswered questions.
Right, so that's the halftime show, and now we'll see the sports. And so mathematics is the one place where it's good English to say I is in the Mandelbrot set. And so here is the score. We have a five-way tie for first between Kyle, Stefan, Erica, Jack, and Cynthia, and then Thomas has 700 right behind.